Joe, is that your real? No, but is that your real house?
It is, but I'm not in the front
Nice.
yard.
Yeah.
That's a picture. That's a picture.
Okay, you ready to go?
That's amazing. That's great. All right. Well, welcome one and all to the general meeting of the Los Angeles Astronomical Society on this date, June the 8th, in the year of our Lord 20 and 26. Welcome. Clappers. All right, I'll take it. As is tradition, we'll start right off the bat asking if we have any new members in-house or not in-house. You raised your hand slightly. All right. Stake your claim, sir. What brought you here?
Well, I'm a small STEM science and math content creator, and I was here for like 3 months last year, attended a bunch of star parties and stuff like that, and really enjoyed it. And so I'm back this time and a member, and I just like all things astronomy, black holes, relativity, you name it. And yeah, I'm just really excited to finally be a member and interact with everyone and attend lots of events. Yeah, seems fun. Yeah. Oh, sorry, Aditya. Yeah.
I should have pushed it away. That was a mutual fault. Anyone else that is new? Or just, what about someone that's old, like super old? You, sir. I can't help it. I can't help it. Oh, no, it's all right. Stay there. Stay there. I have to take shots at Tim. It keeps me young. Yeah. I know. If a shoe comes wheeling in from outside of Zoom and hits me the side of the head.
You deserve it.
Shoe. I do deserve it. I do deserve it. I'll wear it proudly on the side of my face. Okay. Well, what about in Zoom? Is there any new persons out there that wish to make themselves known? Going once.
Mic on.
Here I can hear.
Okay. Well, what do we got? Did somebody say something?
Hello.
They did. Hi. Who are you?
Yeah, I'm sorry. I'm trying to get my camera on. I'm not at the best position here, but hi, my name is July. I'm July Candia. I know Jack, so we were just on the meeting for the Denver Astronomical Society. So I'm working right now in Southern California on a temporary assignment, and of course, astronomy is my passion. So wherever I go, I try to join the club and participate in some activities, and I'm hoping to join everyone for a star party soon.
Well, awesome. That's great. I'm going to be listing all of the stuff we have coming up this month at the end of this meeting.
Great.
So
Thank you.
have plenty of opportunities. All right. Well, as is tradition, I will announce the agenda, which is to go straight to our speaker, then the speaker's Q&A. We'll make some announcements. I will announce the recipients, plural, for Good Heavens this month.
With this also?
Give
Yeah.
away some door prizes.
Yeah,
I'll list a
I
schedule of
can't.
events.
I have no idea what the hell's going on.
You're going to know what's going on. You're going to know all about it,
I
Mike.
could copy and paste it in because of however they sent it.
Yeah. Or I have to use the headphones.
Well, I can put those on now,
Why
but
don't you just?
Mom wants to listen
Spencer,
with
go ahead and
you.
do the
Yeah.
thing.
So let me try to.
Sorry. Need to have this.
Awesome. Okay, fantastic. Moving forward, let's announce the speaker, and for that, I present to you our Vice President, Laura May Abrin.
Thank you. Hello, everyone. Our next speaker is amazing. She is a colleague of mine here at the observatory. She's called Denise Valadez. She's a PhD student in physics at Purdue University, where she conducts NASA-funded research in lunar science under the advisement of Dr. Dave Minton. Now, her work combines computer simulations with observational data from NASA's Lunar Reconnaissance Orbiter, LRO, to study how impact cratering has shaped the moon's surface over time. She also works as a museum guide at Griffith Observatory, where she enjoys engaging with visitors about the Apollo and Artemis missions. Previously, she earned her Bachelor of Science in Physics from UCLA, where she contributed to paleoclimate reconstruction research with Dr. Tripathi, studying regions including the North Pacific Ocean, Southern Oceans, and Amazon River. Denise has also completed internships at NASA's Jet Propulsion Laboratory, JPL, General Atomics National Fusion Facility, and through the GEM Fellowship Program. At JPL, she researched ice sheet modeling and sea level rise under Dr. Schlegel, and later studied origins of life chemistry with Dr. Lori Barge by simulating conditions on Ceres and early Earth. At General Atomics, she worked on plasma physics research related to the D3D tokamak and K-star, contributing to projects focused on plasma stability and renewable fusion energy. Outside of research, she enjoys hiking, roller skating, and playing games like, hopefully I pronounced this one correctly, Pokotopia? Yay! Please welcome, everyone, Denise Valadez. Oh, do you already have a mic? Okay, perfect.
Okay. Can everybody hear me okay? Hello? Okay, so thank you for that wonderful introduction, Laura May. I am so elated to be here with all of you tonight and to share just a bit about my lunar research on the South Pole. And so my whole plan here tonight is to essentially walk you through a timeline of lunar science and lunar exploration. I plan to highlight a few key missions and some major discoveries and how this together, oh crap, I don't even have my presentation up. I'm sorry about that. Can you see that? Okay, perfect. Sorry about that. Okay, so highlighting key missions and major observations and discoveries and how this together has continuously reshaped our understanding of the lunar South Pole. From there, I will be discussing open science questions with regards to the lunar South Pole, as well as knowledge gaps and how we plan to fill those knowledge gaps with the upcoming ARTEMIS missions. Oops. And from there, I'm going to explain how my research directly attempts to inform the science for the upcoming ARTEMIS missions. So starting from the very beginning, the moon has been the Earth's companion for billions of years. And so since the beginning of humankind, we have always been able to reliably look up at the sky and see the moon, right? And one of the brightest celestial objects in our night sky. And so ancient civilizations would look up at the night sky and view the moon, and they would notice changes in shape and brightness. So here's kind of just a depiction of those variations of the moon's phases or cycles. And so ancient civilizations were able to track the lunar cycle, and that's actually where our concept of a month comes from. It comes from tracking the phases of the moon. So essentially, ancient civilizations were able to use this as a natural timekeeper. So some ancient civilizations that I can think of that utilized the lunar cycle were the Greeks, the Romans, the Chinese, for example. One group in particular that I would like to highlight were the Zapotecs. So the Zapotec were indigenous Mesoamericans. And so recent discoveries have pointed to them also tracking the lunar cycle in these encryptions, as you can see here. And so apart from being a very useful natural timekeeper, it's also been very useful in navigation. So for example, navigating Earth's oceans or seas, for example, you need to be able to orient yourself. So when you're in the middle of the ocean, it can be very difficult to orient yourself because imagine all you see around you is ocean, right? And so when you're navigating, you need coordinates to know where you are. So you need latitude and you need longitude. So latitude gives you that north to south and longitude gives you that east to west. So relatively speaking, latitude is relatively straightforward to calculate. However, longitude was actually a long-standing problem in navigation. So it was difficult, so much so that so many men were lost at sea trying to calculate longitude. So because of the miscalculations, unfortunately, a lot of lives were lost. But luckily, someone came up with the idea of using the moon as a reference point because the moon moves in a reliable, predictable way across the sky. So they were able to use this as a reference point to essentially solve the longitude problem. So go moon and math. Okay, so next. So in the previous slide, I essentially depicted the moon as sort of necessary for human progress and survival. However, another very important function of the moon is that it has sparked natural human curiosity. So ancient civilizations looking up at the moon with their very limited knowledge would come up with stories and legends and myths to try to describe what they were seeing in the night sky. Fast forward to the invention of the telescope. So the telescope really revolutionized our view of the moon. And so starting in 1609, an Italian astronomer by the name Galileo pointed his telescope to the night sky. And this is what he saw here. So here we see his first telescopes depicted here. And here are his depictions of his observations of the moon. And some of the features I would like to point to your attention to is that we have these bright and dark spots. So the dark spots we refer to as the Maria, which is Latin for ocean. And that essentially comes from the fact that we thought that the moon had oceans in the past. And the other very, very notable feature is we had this rugged, rough terrain, and we have a bunch of craters on the lunar surface. So around a similar time in 1665, another astronomer, English astronomer by the name Robert Hooke, pointed his 30-foot telescope to the night sky, and this is what he observed. So as you can see these craters here. The biggest crater outlined here is actually Hipparchus crater. So Hipparchus crater is a crater of diameter around 134 kilometers. So it is a very large crater. So Robert Hooke, apart from making extensive observations, also took it a step further and began to theorize, well, where are these craters coming from? What is creating these craters? And so his early theories were that they were a result of volcanoes, so volcanic activity creating these craters, or a result of impact, so meaning things smashing into the lunar surface and creating these craters. So fast forward to the modern era. So here I am defining the modern era as the period from the 1950s to the present day. So I essentially highlighted for you all of the major missions that we have sent to probe our closest neighbor, the moon. So many missions, and I put this here just to kind of showcase the effort and the time and the amount of resources that we have put into trying to better understand our closest neighbor, the moon. And so for the sake of time, I will not go into every single mission, I do apologize, but I am going to cherry pick just a few that are the most relevant to my research. So I'm gonna start with the Apollo missions here, and then I'm gonna work my way to the Clementine missions, followed soon after by the Lunar Prospector mission, and then together the Lunar Reconnaissance Orbiter and LCROSS, and then ARTEMIS, which is our current effort to go back to the moon. Okay, so essentially the picture that I'm gonna paint for you is how our view of the moon has changed from the Apollo era view of a dry moon to now our current interest in the South Pole because there is water ice, which is the current target of the ARTEMIS missions. Okay, so I'm gonna start from the present day and kind of motivate a little bit of my research before going through the extensive timeline. So here are just a few of the major ARTEMIS mission objectives. So we have long-term presence on the moon, we have South Pole science we want to do, and we have moon to Mars. So with the long-term presence on the moon, the whole idea is that we want to build a lunar base. And so with building a lunar base, there are a lot of technological difficulties that we are going to face in trying to achieve that. And so just some of the difficulties I can think of are the lighting and the terrain. So because of the location on the South Pole and how the sunlight hits, we have these things called permanently shadowed regions, so where the sunlight never hits. So in those regions, it would be very difficult to utilize things like solar powered like electricity, for example. So you cannot use the sun to power your equipment if you can't see the sun, right? And you also have very dramatic temperature variations at the South Pole, which would also make it very difficult. We also have extreme terrains. So what I mean by that is you have very dramatic elevation increases. So you have these really huge mountains, and then you have very, very deep craters that go like kilometers deep, for example. So very stark contrast in terrain on the lunar South Pole. Okay, so next, the South Pole science. So there are a lot of open questions about the geologic history of the early lunar surface. And the South Pole is actually the location of the oldest basin, the South Poican Basin. And when I say basin, I just mean like a really extremely large hole in the ground. So the South Poican Basin is around 2,500 kilometers, I believe. And so because the South Pole, it has the most ancient terrains, we believe that essentially we can find answers to these very tough questions about the early geologic history of the lunar surface. The other very big motivation is that we believe that there is water ice at the South Pole. And I would argue that that's a bigger motivation currently because of the resource utilization of water ice on the South Pole as well. And then next we have the Moon to Mars. So NASA has this thing called Moon to Mars architecture, and essentially what that means is that we have a roadmap where we are trying to go from building a lunar base and a long-term presence on the moon to then having our first footsteps on Mars. So essentially, the Artemis mission is a key milestone in trying to achieve that Moon to Mars architecture. Another thing I wanted to mention is NASA is also spearheading something called the Artemis Accords. So the Artemis Accords are essentially a non-binding guidelines for space exploration and peaceful use of the moon. So because NASA is not the only nation to be going to the South Pole or attempting to go to the South Pole, essentially this set of guidelines is meant to try to keep global peace across like countries. So to date, I believe the last time that I checked this, 67 countries to date have signed the Artemis Accords. So essentially, the major takeaway behind all this and the Artemis mission objectives is that there is a lot of like rich, promising science in the South Pole, and there is a lot of technological difficulties. So it's essentially like a high risk, high reward type of mission. Okay, so now I'm gonna take a giant leap back to the Apollo era. So the Apollo program was NASA's first effort to put a man on the moon. And so the primary motivation behind this was the space race. And so between 1969 and 1972, 6 missions would land a man on the moon. And you can see those missions here at the very center. So we have Apollo 11, 12, 14, 15, 16, and 17. And just to address the elephant in the room, Apollo 13 did not successfully land on the moon. However, that crew was able to return safely back to Earth. If you have not watched the Apollo 13 mission, I would highly recommend it. I really enjoyed it. Okay, so back to the Apollo 11 mission. The Apollo 11 mission would land the first men on the moon, so Neil Armstrong and Buzz Aldrin. And these were the famous words of Neil Armstrong: "That is one small step for a man, one giant leap for mankind." And so this would inspire future generations of astronauts, of astronomers, of scientists, of engineers. And here we see these marvelous pictures. So we have Buzz Aldrin right next to the American flag. And we also have this famous footprint image on the moon, the lunar surface. And then we also have images of astronauts essentially collecting samples in these tubes. And then here are some images of some Apollo samples that we brought back. Okay, so another note I wanted to make is that with the Apollo sites, they were chosen around the equator, and that was intentional. So the main motivation was that we wanted it to be as safe as possible, in contrast with Artemis, which very, very difficult terrain to maneuver. So the main priority of Apollo was safety. However, because we did sample within this region, that means that our view of the moon is more or less very limited, and I will go more in detail into that in the subsequent slides. So with these 6 missions, we brought back around 382 kilograms of samples, and analysis of these samples would essentially give us our first look into the geologic history of the moon. And the picture that these samples painted was that the moon is extremely dry place. And this would be our view of the moon for the next 2 decades. And I just want to highlight some of the famous words of the last astronaut to walk on the moon to date. So Apollo 17 astronaut Eugene Cernan, the last man to walk on the moon to date, famously said, "We leave as we came, and God willing, return for peace and hope for all of mankind." Okay. So as I had previously mentioned, we would not go back to the moon for 2 decades, and it wasn't until the Clementine mission that we returned to the moon. And so the Clementine mission was launched in January of 1994, and it was an orbiter. So the Clementine mission was a collaboration between NASA and the Department of Defense. And the main objective behind the Clementine mission was essentially to test lightweight space equipment. So that was the primary objective. However, the outcome would be that it would essentially be testing this Apollo era view of a dry moon. So it kind of just happened when we weren't really expecting. So Clementine gave us this new view of a moon, and it was able to map the entire surface of the moon, including the South Poles. So before the Clementine mission, the South Poles had never been mapped. And actually, when you would look at older maps, they would actually just not have anything for the South Pole, and it would just say Luna Incognita, which just means unknown moon. So Clementine really was amazing in giving us this holistic global view of the moon. So Clementine essentially would give us 1.6 million images, and it would make these observations spanning wavelengths from the UV to the infrared. So I did put for your reference, these were the ranges of wavelengths that Clementine was making its observations. So apart from making these observations, it was able to use this multispectral data in order to create this albedo map of the moon. And essentially what I mean by albedo is the reflectance of the radiation. So if you have high reflectance, that means you have high albedo, and if you have low reflectance, that means you have low albedo. Yes. And so the other thing that Clementine did was this method called laser altimetry. So that essentially means that all it did was bounce laser pulses off the surface. And from there, it was able to get topography graphs. So what I mean by topography is that whether those signals went into like a deep crater or a mountain, for example, so you're getting like those elevation points deduced by the data. So some of the major discoveries or milestones of the Clementine mission was in mapping the South Pole, we found these things called permanently shadowed regions. So this is a permanently shadowed region, which means that the sunlight never hits. So the moon has permanently shadowed regions because of its obliquity. So what I mean by obliquity is its angle between the tilt and then the plane at the equatorial plane. So that angle is very low. So it's essentially at an 88-degree angle. So because of that angle, you have regions that the sunlight never reaches, right? So this is just one example of that permanently shadowed region. And then the other major discovery of the Clementine was Clementine also did something called a bistatic radar experiment. So essentially it sent out radar signals, got back that pulse, and interpreted that signal. And the signal that it interpreted essentially hinted at the possibility of ice or like a lunar volatile. So when I refer to something like a lunar volatile, what I really mean is that it can evaporate at low temperatures. So it can be relatively unstable. So water ice, if I say lunar volatile, I'm using that and water ice kind of interchangeably in this talk. Okay, so essentially Clementine again began to challenge our view of a dry moon. But people were not convinced, and so we sent another subsequent mission fairly soon after, like only 4 years later. So we sent the Lunar Prospector mission. So the purpose and motivation behind the Lunar Prospector mission was to verify the past findings of Clementine. So Lunar Prospector was an orbiter that was launched in January 7th of 1998, and it would orbit around the moon, mapping the moon for 19 months. So there was multiple instruments on Lunar Prospector, but I'm going to focus on just one here. So I'm going to focus on the neutron spectrometer aboard the Lunar Prospector. So essentially what we have here is we have this cosmic ray. So cosmic rays are constantly interacting with the lunar surface. So when this cosmic ray interacts with the lunar surface, there is a outward flux of epithermal neutrons. So the neutron spectrometer is somewhere like nearby, essentially measuring and taking data of this outward epithermal neutron flux. So that is what it's measuring. So based off the epithermal neutron flux that the neutron spectrometer observed, it essentially deduced that these epithermal neutrons were interacting with potentially hydrogen here on the surface, that there is some hydrogen presence here. And so they were like, okay, hydrogen, so that means that there could be ice, right? But again, people were still not convinced. They're like, well, how do we know that it's actually like ice? Hydrogen doesn't mean ice. So we needed further proof. But before I get into that, I just want to mention that at the very end of this 19-month-long mission, this Lunar Prospector probe would be actually sent to go collide into Shoemaker Crater. And Lunar Prospector had some of the cremated remains of late Eugene Shoemaker. So Eugene Shoemaker was a planetary scientist who had a dream of becoming an astronaut. And that dream was crushed when he was diagnosed with Addison's disease. So because of that, he was not able to be an astronaut, but he was very influential and also very vital in the training of Apollo astronauts. So essentially, this was our way of paying tribute to him and allowing him to essentially live out his lifelong dream of going to the moon. And that is why we also have this crater called Shoemaker, which is one of the permanently shadowed regions on the lunar south pole. Okay, so as I had mentioned, the Lunar Prospector mission outcomes was still heavily debated. So it's like, no, we need more. So close to a decade later, we sent out LCROSS. So LCROSS, which stands for Lunar Crater. I'm sorry, I'm like blanking on like the full acronym, but essentially, it is something that we sent to go crash into a crater, essentially. NASA loves their long acronyms. I apologize. So the main purpose behind LCROSS was essentially to crash into a crater, excavate material, and bring that to light, and then make observations to see, okay, is there potentially water within the crater, and can we excavate that and see that, right? So as I mentioned, LRO and LCROSS were sent together. So before LCROSS collided into the crater, LRO essentially did a mapping of temperature. So LRO identified a prime candidate. So it took temperature measurements and it saw, okay, Cabeus crater is a very good candidate for this crash mission. So LCROSS was sent to Cabeus, but it was also attached to something called a Centaur stage. So the Centaur stage was sent first to collide into Cabeus, and then after that, LCROSS followed soon after, like minutes after, and it flew into the ejecta plume that was essentially freshly created by the Centaur stage. And I do have a video of this in the subsequent slide just to show you so you can see it for yourself. But the essential outcome of this is that they did detect water ice in the plume, which is very exciting. So again, we're building that very strong case for water ice presence on the lunar south pole. So I'm just going to play this video here. So as you can see here, that's the Centaur stage that's going to collide into Cabeus crater. And then soon after, we're going to see the LCROSS following soon after. So there we have LCROSS. So we have this ejecta plume that's coming out, and LCROSS is ascending into the ejecta plume, and it's taking measurements right before it collides. And then LRO is somewhere nearby hanging out, also taking measurements. So we have a double verification of the presence of water in Cabeus crater, which is very, very exciting. So as I previously mentioned, the Lunar Reconnaissance Orbiter was also sent with LCROSS back in 2009, and it's still currently functional today, so still orbiting the moon periodically. So LRO is our longest standing orbiter around the moon, and the main objective of LRO is it's continuously mapping the moon with multiple instruments. So we have multiple instruments that are constantly mapping, for example, the temperature and the topography. And LRO has been very vital for ARTEMIS mission planning because it's been able to map at very high resolution the permanently shadowed regions, the temperature, and whether we think that there are water ice within certain regions. So all of this is deduced from LRO. And it's also vital for future science exploration as well. So it doesn't just stop at ARTEMIS. It's an instrument that just keeps on giving, and I would argue it's my favorite. So here we have LRO, and then here right before launching, these are just some acronyms for a lot of instruments on LRO. And this is just one example of a colored topography graph. So these very purple regions are essentially very, very deep. And then these green regions are very like high. So you can kind of see the schematic here. So very, very dramatic changes in topography. So just to make sure that we are all on the same page, I'm going to summarize essentially what we just talked about some of the various missions. So through Clementine, we essentially had a global first view of the moon, and we were able to map out permanently shadowed regions, right? So we were able to see that permanently shadowed regions exist. And then through Lunar Prospector, looking at the signal of epithermal neutrons, we were able to deduce, okay, that means that it could be interacting with hydrogen, which then could point to ice. And then with LCROSS, essentially we were able to validate presence of water within these permanently shadowed regions. And then LRO is continuously mapping the moon. Okay. Okay, so next I kind of want to go through some open science questions on the South Pole. So now that we more or less have kind of like established that we feel like with 90% certainty that there is water ice at the South Pole, now the question is kind of shifted to what is the abundance and distribution of water ice? So how much of there is it, and is it distributed evenly, or is there some sort of like trend that we notice with the distribution of water ice? And so the other open question is, with these permanently shadowed regions, how old are they and how stable are they, right? Because in knowing the ages of the permanently shadowed regions, that could indirectly kind of help us resolve, okay, what are the ages of the ice? How long have the ice been there? Is it a recent delivery, or is it like something ancient that happened long ago on the moon's surface? And then finally, the third open question that is still ongoing is what locations on the South Pole are both very accessible and will maximize our scientific return? So we want it to be relatively safe enough, and we also want to be able to return as much science as we can. So now that I've roughly gone through some of the major missions in understanding the South Pole, I'm next going to go on a bit of a literature dive and explaining some papers that essentially have made key interpretations of the Lunar Reconnaissance Orbiter data and how that is essentially fed into my research project. So the first paper that I essentially wanted to discuss was on the South Pole, and essentially the main motivation behind this paper was to map out the temperature and the UV albedo of the lunar South Pole. And so the first author of this paper is by the name Paul Hayne. So Paul Hayne is a planetary scientist at CU Boulder, and he's been involved in various NASA missions, most notably the Lunar Reconnaissance Orbiter. So he's very involved with the Diviner instrument, which, if you recall, that measures temperature. So the main objective behind this paper was, okay, if we look within the permanently shadowed regions, where is the ice, right? And where the ice is, can we see if there's a temperature dependence on that ice? Okay, so the observations that he used in order to get these plots, again, were from instruments on the Lunar Reconnaissance Orbiter. So he used data from Diviner. So he used Diviner to obtain temperature, and then he used an instrument on LRO called LAMP. So LAMP stands for Layman Alpha Mapping Project, and he utilized that in order to get the UV albedo reflectance. Okay, so just to kind of orient yourself on this plot, notice these three craters in a line. So this is Howarth, Shoemaker, and Faustini. And so this is essentially our temperature plot. So notice that on this temperature bar here, we have T max. So this is the maximum temperature annually that we see on the South Pole. So notice that only a few craters, most notably these craters, the entire year stay relatively cold, and then other regions of the South Pole do warm up for certain times in the year. And then in contrast, we have this other plot here. So notice the T average temperature scale bar. So the main takeaway here is that on average, most of the South Pole does stay relatively cold. But the key here is that only some craters remain pretty cold throughout the entire year. So now let me point you to this graph here. So this is essentially based off the UV albedo reflectance spectra. We see only patches of ice. So essentially the observations were deducing that these could be the regions that have ice on them. And so the main takeaway behind this paper is that we believe that there could be some temperature dependence of whether a PSR can maintain lunar volatiles or water ice in them. So that is the major takeaway. And then we will lead on to the next paper. So this paper essentially is trying to investigate and find, is there a relationship between the ages of permanently shadowed regions and the accumulation of ice that we see? So the author of this paper is Oded Aharonson. So he is a planetary scientist at Weizmann Institute. And so just to note here, the second author of this paper is Paul Hain. So Paul Hain, this is actually building off of the last paper that we actually just saw. So this is actually the data set from the previous paper. So we're essentially building up and continue to build this research. And so again, we're using Lunar Reconnaissance Orbiter data. And as a reminder, the last paper, we said that there could be a temperature dependence on the ice presence within the permanently shadowed regions. Now with this paper, what they're trying to ask is, well, what is the history of that ice? And is there a link between the ice area fraction, which means just the ice within a certain area, and the ages of the permanently shadowed regions? So how they do this is they use the observational data, which is here, and they compare that with a model that they create to try to obtain the permanently shadowed region ages. And how they get those permanently shadowed region ages is they actually connect the geometry of the permanently shadowed region and the lunar obliquity. So what I mean by that is there has been extensive studies that have showed that the lunar obliquity has decreased over time. So we believe that it was actually higher in the past and it has decreased significantly. So what that means is that all the permanently shadowed regions that we see currently were not always permanently shadowed regions. Some of those are actually relatively new or younger than older ones. So using this sort of like a link between lunar obliquity and the geometry of the PSR to deduce, okay, at what lunar obliquity angle will we have it remain in shadow, he was able to get these ages of PSRs. So I'm going to point you to this plot here. So we have the PSR ages, and then we have the data. So these orange dots are the data points from LRO, and the black solid line is the model ages of the PSRs. So I want to point you to two kind of important trends here. So the first trend is between 3 to 3.5 billion years ago. So within this range, we see a dramatic increase in ice. So we think that there could have been some ancient sort of like lunar volatile delivery. So some mechanism could have delivered ice to the surface around this time period. The other trend I want to point you to is the one from 1.5 billion years ago until now. So between 1.5 billion years ago until now, what it seems like we're seeing here is that there is a trend between the PSR age and the ice accumulation. So what I mean by that is that in the past 1.5 billion years, there is a link between the age and the ice, which means that older PSRs have more ice and younger PSRs have less ice. And so what this suggests is that there might be some mechanism that is constantly supplying the ice as we're seeing, as suggested by the data. Okay, so that is the major takeaway here. And so the next paper, which is the final paper that I'll go into before going into my research. Next, we have another paper by Caleb Fassett. So he is a planetary scientist at Johns Hopkins University, and he's also been involved in various NASA missions. And so the whole motivation behind this paper was that he wanted to kind of catalog the population of craters around the permanently shadowed regions on the South Pole. So how he did this was he actually used a machine learning algorithm in order to build this crater catalog. So this is, all of these like yellow dots you see here are essentially like, the machine learning algorithm detecting craters. So he used two things. He used the Lunar Reconnaissance Orbiter data, the LOLA data, which is the topography data, and he also used a human catalog, so meaning like past catalogs, in order to train the machine learning algorithm to be able to detect craters. So I believe that around the first time that he did this, like it actually did a terrible job. But then once he started training it a lot better, it actually went to like very high accuracy. So that's very promising. But essentially this cataloged 21 million craters of diameter greater than 10 meters. The other very important takeaway behind this paper was that he was also quantifying lifetimes of permanently shadowed regions. And what he deduced is that larger craters will be able to stay within permanent shadow longer than smaller craters. So smaller craters will not persist as a permanently shadowed region for as long as large craters. And his justification for that is that small craters erode off the lunar surface much faster than larger craters. And there's been extensive studies that have showed this, so if you would like any paper recommendations, I'm more than happy to pass those along. But essentially, the motivation behind trying to get some limits on the PSR ages is that then we can also indirectly place constraints on the volatiles themselves, right? Because the volatiles or the water ice is within the permanently shadowed regions. Okay, so just to make sure we're all on the same page, I'm just going to quickly summarize the main takeaways behind the last three papers that we just discussed. So with the first paper, as a reminder, looking at observational data of the South Pole, we were able to look at permanently shadowed regions, and we deduced that in order for a permanently shadowed region to have ice, it has to maintain a temperature of below 110 degrees Kelvin. The second paper, we were able to connect the thermal history of the moon to the lunar obliquity, and through that, we were able to see a link between permanently shadowed region ages and ice accumulation. And with the third paper, we were able to look at permanently shadowed region crater populations and permanently shadowed region ages and how that could then tell us something about the lunar volatile delivery mechanisms, for example. Okay, so as I mentioned with the last paper, because there is an emphasis on permanently shadowed region stability linked to the size and the evolution of the crater, well, what better way to try to look at permanently shadowed region crater stability than with some fun simulations? So in modeling the South Pole, I essentially utilize a code called Crater Maker. So Crater Maker is a community code. It is open source, so you are more than welcome to play around with it if you'd like. That is the QR code to the GitHub for Crater Maker. It's meant to be user-friendly, so if you're having issues with it, feel free to message me. But essentially, I use this code called Crater Maker, and it's a Monte Carlo landscape evolutionary code. And so Monte Carlo essentially means that cratering, we treat it as a randomized process, which is why we are able to say, okay, it's a Monte Carlo process, so we're using a Monte Carlo code. Okay, so as I mentioned, open source, and the code itself is primarily managed by my research group. So my advisor, Dave Minton, is the primary code developer, but myself and other lab mates have been extensively contributing to the code development as well. And so in order to go into the simulation inputs and how I set up my simulations, I will first explain kind of what are the basic assumptions that we're making in this Monte Carlo landscape evolutionary code. So the first assumption we're making is that primary impactors are a result of asteroid impacts. So essentially things from the asteroid belt are hitting the surface continuously. So that's the first assumption. The second assumption that we're making is that larger craters are much, much less probable than small craters. And this is all corroborated based off like observational data that we've received and analysis of Apollo samples as well. And the other assumption is that as time passes, you will have more crater accumulation. So more time is equals to more craters. Okay. So next I will go over my simulation setups, how I set up my South Pole simulation and what are the inputs. So essentially you need a few set of parameters. You need your target, so what are you targeting, right? And then you also need to define the impactors. So what is doing the impacting and what is the target surface? So CraterMaker is designed to be utilized across like various planetary bodies across the solar system. For my main purpose, I'm using it for the moon, but by default, if you do not define the target, then it's gonna automatically say that it's the moon. And so the impactor population by default is given by the Neucom production function. So the Neucom production function is like a function that's derived based off observational data, and it's calibrated using Apollo samples. And then the other thing you need to define is your time. So for the purposes of my simulation, I'm running these for around like 4.3 billion years ago until the present day. And your resolution. So with CraterMaker, you have the ability to do a global run of the moon, so the entire surface of the moon, or you can do local region simulations of the moon. So because my target is the South Pole, I'm specifically doing a high-res local simulation of the South Pole of the moon. And then from there, as I had mentioned previously, CraterMaker is a purely Monte Carlo code. However, you do have the option to make it quasi Monte Carlo. So what I mean by quasi Monte Carlo is you can make it partially Monte Carlo. So what I'm doing in my simulations is I'm inputting a set of permanently shadowed regions into the code, and I'm saying, okay, I want these specific craters around these specific times, but everything else, all of the rest of the crater population can be randomized. I don't know if you guys recall from the previous slides, those 3 craters in the line, for example, Faustini, Shoemaker, and Howarth. So those are essentially some of the inputs of PSRs that I'm putting into my code. So with these models, I'm essentially doing 2 things. So the first thing I'm doing is I'm actually testing the permanently shadowed region ages as deduced by Caleb Fassett's last paper, so the last paper we went through. So I'm testing his PSR ages into my code, seeing what that gives me. And the other thing I'm doing is I'm also deriving age estimates for the permanently shadowed regions myself. So I'm testing past work, but then I'm also deriving them, and then I'm going to do a comparison study between the 2. Okay. So here are just some preliminary results to my simulations. So on the right here, we have observational data. So this is data, again, from the Lunar Reconnaissance Orbiter of the South Pole region. So we have the scale bar of around 50 kilometers, but I believe this is like around 150 kilometer by 150 kilometer area that I'm looking at. And I also set up my simulation parameters to be around the same. So let's see here. I'm trying to play the video here. So this is like a video animation of the past 4.3 billion years. So very cool, right? We're seeing craters happen. I'm more than happy to play it again. More than happy to play it as many times as you'd like. So as you can see here, and I'd like to kind of rewind just to emphasize this, but again, we're using the Neucom production function as our impactor population. And this impactor population, again, using the calibration of the Apollo samples, suggests that at the very early evolution of the lunar surface, we had impacts which were much more frequent, and they have since slowed down. So that's kind of why all the action is happening within the first million years, and then after that it kind of just slows down and you kind of have to wait to see more craters appearing. So yeah, this is all based off of that production function that I input into my simulation. But the code itself does have an option for other production functions as well, or user-defined even, which is great. So these are essentially my preliminary results. And so now I'm just going to go through some of the implications of this. So with the ARTEMIS missions, we have 9 current candidate sites, so around permanently shadowed regions. And so again, we want to maximize accessibility, but we also want to maximize the science that we are doing there. So in better understanding the stability of the permanently shadowed regions, then we can build better cases for which permanently shadowed regions we should be visiting. Again, because it's still on the table and it's still being debated where we should go and where we can maximize the science. So with my simulations, what I'm hoping to achieve is to motivate and testing the stability to see like, okay, where can we maximize the science in these ARTEMIS missions? So that is everything from me. So just a few acknowledgements. I'd love to acknowledge my advisor, Dr. Dave Minton, for being very supportive throughout my PhD. I would like to thank the NASA LDAP, so the NASA Lunar Data Analysis Program, for funding my research. I would also love to thank all of the mentors that I've had across my academic journey. I would not be here without the extensive mentorship that I have received. I would also like to thank my friends and family for their continuous support as well. And thank you. And if you would like to contact me, there is my email. Thank you. Of course. Can I just stand here?
Questions? Yes. Okay.
Okay, before the question, nice talk. I liked it.
Thank you.
And,
Thank you. I appreciate it.
My question is, how do you make the UV albedo measurements in the bottom of the craters where the sun doesn't shine?
So that's a very good question, and I'm not directly involved with the actual like data collection and the actual interpretation of the data. I just read this very useful paper by Paul Hain, and so he essentially did all of the heavy lifting in trying to make interpretations of the UV albedo data within the permanently shadowed regions. Yes, but I can refer that paper to you if you would like.
Are you planning on doing any more simulations? And if you are, like, what would you change on your next run?
So that is a very good question, and this is just the beginning. So I will be running these simulations hundreds of times more, probably. So as I mentioned previously, this code is in development, so it actually has come a very long way in the past year. So we actually were just able to implement quasi Monte Carlo runs within the past like 2 months. So this is still relatively new, and yeah, I do plan to run suites more of simulations. Some things that I want to play around with are what production functions I'm using. So as I had mentioned, the default is the Neuquén production function, but I also want to utilize the Robbins production function as well. It's not as accepted in the lunar community, but I do think that it makes some valid cases. So I would actually also like to use that and see how it influences my simulations. Also, these are rough estimates of the PSR ages, so I feel like there is still much more work to be done to actually try to constrain these PSR ages, which are then inputs to my simulations. Yes, but thank you for your question.
Hi. 2 questions. First is, you mentioned that younger craters might erode, and I was wondering what the mechanism would be for eroding a crater on the moon. And second question is more of just a point of curiosity. If there are permanently shadowed regions in the south, does that mean that there are permanently lit regions on the north?
So that's a very good, so both very good questions. So to address your first question, there is actually, and I did not actually go in technical detail in my talk about this, but with another kind of key parameter in our simulations is also taking into account the way that craters degrade, right? So what are the degradation mechanisms? Because craters are not going to stay on the surface forever, right? So on the lunar surface, one of the primary degradation mechanisms for degradation of craters is more craters. So that's kind of the main mechanism. But there's multiple ways that craters can erode on the moon. So I do not have a visual on me, but I can name two mechanisms. So we have one called sandblasting and the other one called cookie cutting. So sandblasting is essentially when you have a very large crater and then you have a bunch of small subsequent craters essentially erasing the rim. So that mechanism is called sandblasting of the crater. So essentially, eventually you won't see the crater rim. And so that's one mechanism. The other one is cookie cutting. So imagine you have a region with a bunch of small craters, and then you essentially blast like a very large crater on top of that. That's cookie cutting. So essentially, you've kind of erased that history of those small craters that were on the surface because of this very large crater that essentially kind of just erased it. Yes.
Thank you for the lecture. I have a two-part question too. My first question is, with these PSRs, is the ice thickness, if we would take like an ice core sample, is it really different at each section of the PSR, would we think? Or if we go close to a region where there's like the Terminator line where there's a light region or with high albedo to a dark albedo, would it be different thickness of the ice? And then my second part question is, in the early region of the early times of the moon, when there was craters being hit, could it have created a volcanoes and the magma come out and become lava and cover up and some newer regions of the moon? And then when a crater asteroid would come, maybe panspermia hit, could it create new craters, and then the old craters look like they're old but they're really not because of volcanic activity?
So if I'm addressing your first question correctly, based off Paul Haynes' paper on like the UV albedo reflectance data, so the LRO data and his interpretation of the data suggests that the ice within the permanently shadowed regions is pretty patchy, actually. So one, he noticed the temperature dependence, but two, he noticed that it appears to be very patchy. So it's not even like doesn't appear to be evenly distributed across the permanently shadowed region. And then there are some permanently shadowed regions that just don't have water ice, for example. And then the other thing, which I did not point out, is it appears that there is water ice outside of the permanently shadowed regions as well. So for the most part, we do link permanently shadowed regions with presence of water ice, but they're not exclusive. So you can also see it outside. As long as you have that requirement of temperature being below 110 degrees Kelvin, then you can have a cold trap, which will preserve the lunar volatiles.
Got a couple more.
Thanks for this great talk. I'm curious, you showed at the very beginning of your simulation all this cratering happening very early on. My understanding is that the late heavy bombardment theory is kind of out now. And so does that represent more of the tailing off theory, or which theory is it in particular?
Yeah, so very, very good question. So because we are using the Neumann production function, that means that we are still, in essence, kind of aligning with the late heavy bombardment with these simulations. But I am in agreement with you that I think for the most part, we believe that the late heavy bombardment may not have occurred. And the reason for that is, so there are multiple reasons, but one that I can just point to at the top of my head is that we believe that there could have been some sampling bias on the Apollo missions, which led to the misinterpretation of some potential spike in the early evolution of the lunar surface. Yes.
And just a second question that also relates to giant impact theory. Do any of your results affect or solve or provide any kind of addition to these discrepancies that we have between, the moon's composition and the Earth's composition, and how the different types of simulations lead to different results and things like that? With regards to the Theia impact, sorry, I should clarify that eventually made the moon.
So do you mean so if I'm understanding correctly, do you mean like how the influence of like the target material or the impactor material?
Yeah, I mean like the fact that, there are discrepancies
Yes.
between what we expected to find in lunar rocks and what we did find. And from what I saw, some of this has to do with also the way the impact happened, and the way the material was kind of distributed.
Yes.
And so do any of your results or work that's being done on PSRs actually help clarify some of these discrepancies? Sorry, is this too convoluted?
No. I guess I'm trying to follow your line of thinking, but what I will say is that at the current state, I do not believe so. Yeah.
It's a totally different kind of thing. That's what I figured. Thank you.
Hi, I was just wondering, it was really interesting seeing the map at the end and next to your simulations, and since you've spent so long studying it, I was wondering if you had any preferences for where you think the Artemis mission should go, and what is kind of the front runner for you?
So that's a very good question, and I can actually go to the 9 proposed landing sites here. So this is essentially me with the mindset of just a scientist, okay? So I'm not even thinking about the difficulty in like managing the terrain, for example. But I do think that it would be worthwhile to go to Cabeus Crater. I think it would be, there is a lot of potential for scientific return there. However, in terms of accessibility, that is still a very open question.
So actually, a follow up on this one. Thanks for the great talk. So what in your simulation would indicate, hey, it's a good target, versus what in your simulation would say, not so good target?
Yeah, so that's a very good question. Thank you for your question. So just referring back to the past papers, there's a suggestion that the stability of the permanently shadowed regions is affected by the way that the craters evolve over time. So my simulations are essentially able to quantify that change, or that evolutionary change in the topography, because if you think about it, if you have like smaller PSRs versus larger PSRs, the smaller PSRs, we can study the way that they're going to degrade over time, and then that'll essentially tell something about the stability and then the lunar volatile delivery. Now, my simulations are mostly focused on PSR stability related to the changing topography, but then from there, we are actually going to work with a collaborator, which is then going to plug this into their thermal models. So from those thermal models, then that's actually when we will actually be able to get more valid results for like potential sites where we could maximize the science. So I'm essentially fitting in like the topography changes into this PSR stability question.
That was an amazing talk. Thank you so much for your time. What technical improvements would support your research the best? Like increased resolution MRO, the runtime for your simulations? What would help your research the most?
That is a really good question. So with my simulations themselves, they are very like data intensive and very heavy, because you are running simulations that are like billions of years essentially. Let me think about that. So there are like 2 limitations we have. So we do definitely have the limitation of the LRO data itself, but then we also have the limitation of like computation power. So like if it's too computationally expensive, and it will take like too long to run. So there's kind of like that give and take between like, yeah, I'm like trying to think about that. That's a good question.
Spencer, were there any on Zoom? I saw the chat had a couple.
Yeah, there are a couple on Zoom. Hang on, let me scroll up to them. The first one was, is the ice contained at the lunar South Pole considered belonging to all people? And how much ice can a single mission use?
So I cannot speak for all people, but I will refer to the Artemis Accords and say that we are trying to peacefully explore the lunar South Pole. So I know 67 countries that are willing to peacefully share the ice. I don't know. But I don't think I can speak on behalf of the entire NASA on that question.
And the second question is any third-party AI being used to help with the crater mapping and planning of potential exploration and ice harvesting?
So not in the current day, but again, I am using the PSRH estimates from the previous paper, which I believe Caleb Fassett used machine learning, but I think that he also did disclose that he also used AI. So I think maybe indirectly by using those results. I don't know if that counts, but not in the present day with our current simulations.
All right, go for
it. I wanted to piggyback on actually the question about water, because earlier you mentioned Shoemaker. We actually sent remnant, or ashes, I should say, of Shoemaker.
Yes.
Because I remember that recently there was some billionaire who was trying to have his ashes sent up there, and that seemed to have been a big no-no, because obviously the moon belongs to everyone, and we don't want to turn it into a graveyard. Is that still the case? Do you know more about? Yeah, I didn't know that that had actually happened, and it surprises me because my impression was that that's not being done anymore.
So, to my knowledge and understanding, Shoemaker is the only person who has had their ashes sent to the moon.
Okay. Yeah.
And I did not know about that billionaire.
Yeah, but it hasn't happened, so.
Yeah.
I can think of a couple living people that I'd like to send.
Is there what are some of the theories of why the north and south lunar poles are so different?
What? Sorry?
There was a question on what makes the North and South Pole so different.
Okay, so I will only speak to my expertise. So currently I am the most well-versed on like the South Pole and the Marias, so I cannot speak for certain why there's a stark difference between the North and South Pole.
So my question is, you're simulating craters, but your goal is to decide where to look for ice. So are you going to add ice to your simulation at some, like the deposition of ice, to compare that with your craters and maybe change your mind about something when you figure out how does ice actually get somewhere on the moon, and compare that to your craters?
Okay, thank you for that question. And I'm sorry if I did not make this extremely clear. But there is no ice in my simulations. So the reason why I covered the current papers that I did was because I was kind of trying to walk us through how our inferred detections from observations about the presence of ice, how that then connects to permanently shadowed region ages, and how we're then using topography and seeing how topography affects the permanently shadowed region ages. So as I had mentioned previously, the piece of the puzzle that I'm contributing is seeing how PSR stability is influenced by the topography. From there, we're going to hand that to our collaborator, who is then going to run it through his thermal models, which is then going to do the comparison with ice. Yes. No, you're fine. Yes.
That can is kicked down the road in advance. Awesome. Anyone else? We got one. Oh, Jeff. What's up, buddy?
Is there an instrument on the LRO that you wish were included in the LRO?
So it's hard for me to answer that question because I feel like I'm so spoiled working on the moon. So a lot of colleagues that I have that work on other planetary surface are not as spoiled with the extensive data sets that I have available to me. So speaking from how spoiled I am, it's very hard for me to try to think of like an instrument that I feel like, and also because the main data sets that I'm working with are the LRO LOLA data. So I'm essentially mostly working with topography. So I feel like if there's any way that we could even like increase that increase that resolution, then that would be like amazing. So if I could make an upgrade to that, I feel like that would be my request.
Yeah, what was your cat's name?
Great question. My favorite question. So his name is Chacho. So my grandmother had a pet pig in Mexico called Chacho. So he's essentially named after, yeah.
So kind of like a junior?
Exactly, because you could see the resemblance, right?
Yeah. I think that cat's giving me the look that
it's feed me now, human.
The eyes follow you wherever you go. Anyone else?
Quick reference, so you know, the cross stands for Lunar Crater Observation
and sensing satellite.
Thank you so much for that.
All right. Thank you very much, Denise.
Thank you. Sorry, I don't know what to do with myself. Like, do I just
How's that?
on mic now or?
Oh, you want to?
No, I'm just asking.
You want to go back into anonymity? Here,
I
there's a switch right there. You can. All right. Excellent. Excellent. All right. So, Spencer, do you want to get into your spiel?
Yeah, hang on just 1 second. Let me cue it up. Okay, here we go. Let me share a screen for 1 second. Do a slideshow. Okay. All right, let me share this. I'm going to give everybody a brief report on the light pollution committee at the LAS. Just to set everybody on the get everybody kind of scared. This is a light pollution map of the U.S. in 2025, and you can see the dark areas are Border 1 areas basically, and so you can see that we have a few Border 1 areas, but mostly in the deserts in Nevada and in Utah and so on. And so this is a slide from another talk I gave in Alhambra. So this gives you a sense of what the light pollution looks like in terms of sky brightness using the SQM, which is what we normally use to gauge how dark a sky is. So what's amazing is that if you look at the trend, it's almost a linear trend, like from Alhambra, where I gave this talk last time. It's increasing about 2.8% per year. And in Joshua Tree, it's increasing about 4.6% per year. So that's compounded. And then there are no Border 1 sites left in California. So that just sort of gives you an idea of where things stand right now. So we've been actively involved in two parallel efforts. So one is LA County was mandated to make updates to their general plan, basically to enhance wildlife protection and open space access. And so when we first looked at this, we realized that there's one mention of light pollution in the general plan. So we've been working with the county and going back and forth, and they finally they agreed to that light pollution is a negative stressor in wildlife. And so now, using wildlife protection as a lever, we're able to get them to include light pollution quite a few times in their general plan. And so just to set expectations, the general plan basically sets broad guidance. It doesn't really set any codes or criteria or rules, hard, fast rules where they can be enforced. But at least that's a step. And so if you're interested, that the draft of the general plan is, especially the part that we're concerned with, is available for public comment until June 30th, and that's the QR code for the link for that plan. So if you're interested, take a look at it. Contact me or Rod Kaufman, and we can get you more information. And there's a link in there at this site for comments as well. So the other effort is we realize that light pollution doesn't really respect jurisdictional boundaries. And so cities like Malibu have really strict night sky friendly ordinances. For example, you can't have string lights outside unless it's for just to have them lit. It's got to be for an event, and when that event's over, then you have to be turned off. And then you have other cities where there's very, very little concern about light pollution. They're more concerned about what they call light trespass, which is light from your from your neighbor hitting your property at night and shining into your bedroom window. So towards that end, we realized that we need sort of a regional effort, and so there's a petition that we've started. There are two versions. There's the hard copy version, and I'll get to that in just a minute, and there's an online version. And so the whole idea is that we want we want to get enough signatures as we can, and then tell the elected officials and the county officials in LA County and say, hey guys, you need to get to collaborate and address light pollution as a regional problem, not just piecemeal like it's being done now. So, and just to close off, this is just as a reminder. I don't think most of us are pretty familiar with what responsible lighting is, but this is just a reminder. And with that, I'm going to Penny. Are you in the audience tonight?
Yeah, Penny's here, and
Okay.
she is full collection mode.
Okay, so I'm going to stop sharing this. So Penny is collecting hard copy petitions. And Penny is actually looking. We're looking for volunteers to help distribute these petitions. We encourage you to sign the petition, and if you want, we can make copies of the petition and take them to your family, to your friends, your neighbors. As many signatures as we can get, the better off we'll be. Because, like I said, we'd like to be able to go to the mayors of the cities in LA County, the county regional planning folks, the elected, all 5 supervisors, and say, hey guys, this is a serious problem we need to address. Light pollution is not going to go away. It's one of the easiest types of pollution to control. So let's get together and see if we can't do something about it. Thanks.
Awesome. Thank you, Spencer. Yeah, Penny's going to be present. Yeah, yeah, and also if you want to help with collecting signatures, you can get a form, and what 2,000 minimum, maximum the whole earth.
And for those of you on chat on Zoom, I'm going to post in the chat. I'm going to post a link to the online version of that same petition.
That is actually in the works. Spencer is going to be making a what's it called again? Spencer, there will be an online version.
The online version
for social media.
Yeah. Yes, I'm posting the link for that in the chat right now. And then I'll send out an email with the links as well.
Thank you, everybody who signed already. Thank you, Spencer. I'm just kind of jumping into this effort at the last minute here, but please take a copy and make copies and get signatures, and you can send it to me via email, kunitani@ucla.edu. And if you have any questions about that, I'll be around after the meeting. We have about 200 so far. I also cannot go to everything, so I am really looking forward to all of you volunteering to cover some of our events. We have lots of events coming up, star parties, Mount Wilson, Lockwood, every Wednesday night at Garvey Ranch. What else? Yeah, everything. So if you're going to go to one of those things, please take a copy and get as many signatures. Make a lot of copies, get as many signatures as you can. Thank you. Anybody can sign. As Spencer said, the light does not know city boundaries or county boundaries. It goes everywhere. And I hope that the county supervisors who will be receiving, all 5 county supervisors will be receiving these petitions. I hope that they are concerned about our visitors because, of course, tourism is really important to the health of our community. Out of state, out of country, those people all bring their moolah to our city, our county. Fabulous, fabulous. And we are going to be asking, thank you, for permission to do it on the lawn here for our star parties.
Do we have
events.
permission? Do we have permission to do that on the lawn?
She said she doesn't know yet. The director. Well, we're waiting for an answer from the director. Yes. Okay. And any other questions? And please raise your hand and I'll pass some of these out. Thank you very, very much.
Do only sign it once. We all want dark skies. Once.
Thank you. I'm sorry. May I add just a little story? So the last month, every year I come here, it's getting worse and worse. Last month was my first time this year, and I looked to the southeast where Santa Clarita is fast developing more and more every year. I could not see a single star below 30 degrees. That is 1/3 of the sky in that direction. I could not see one single bright star or planet. Thank you.
All right. Any other questions? You can meet up with Penny afterwards. Okay, fantastic. All right, Roman. Yep. We got a lot of guests in this one. I almost feel like, if we keep getting this, I need a couch and a desk. Yeah, exactly. Yeah. Here's one.
All right, so my name is Roman Telesnikov. How many of you don't know that we have a robotic observatory for the club? All right, that justifies my existence. I have 5 extra minutes just because of that. All right, so about a year ago, I showed up here, it was in May, and introduced the robotic observatory to the club. So it's been a year, so I wanted to, number one, refresh the membership. We had a lot of people join since then. So this may be the first time you hear about it, hopefully not, but it could be. And just tell you how we've done over the last year of operations. So the vision for the robotic observatory is to bring remote dark sky, relatively dark, trying to get darker, thanks Penny, to the membership and also the public in a way, and also dramatically lower the barrier to astronomical imaging in general, but exploration of the night sky. It started out with this. This is John O'Brien's literal napkin sketch and some hole in the ground. After over a year of work, we ended up with the pretty state-of-the-art robotic observatory. So there is the view of this thing in operations. It's an old pic from last year. And a website that you use, so LAAS-RO, I have QR codes later, that you go to use it. This is not meant to be a talk about how to use it or what to do. There are references there. This is a refresher and a zinger, if anything. We have a state-of-the-art telescope in there. We have state-of-the-art imaging equipment, and it's all made super easy for you to use. I'll talk a little bit about some of the restrictions, provisos, and very high bar that you need to meet to use it. Here's what you get. You get 1,000 millimeters. You get like almost 2 by 3 degree field of view at pretty low resolution. To those of you who are astro imagers, like wide field imaging, this is as good as you're going to get on amateur level. So you should be salivating over this if that's you. If you're not salivating, you should try it. Then you'll really understand, what it's all about. And this is the slide that is actually new. So obviously, I'm following, some extensive researcher here. So I feel sorry for all of you having to see this. But this is how we've done. So this is usage statistics. I'll go over this a little bit because it's fun. So the green wiggles here are the actual available time, which is like the dark sky minus the bad weather. So like here where the red light is like that's where time could have been available if it weren't for rain and clouds. So you see that our weather at the site is actually pretty good. Please ignore things prior to October. We improved our telemetry quite a bit in October, and so we can actually measure it since October. And you can see that a lot of times the green and red lines are actually pretty much the same. Where it drops out, that's when we had seasonal storms and stuff like that. So our weather at the site is actually very good. The blue wiggles is the subscribed time to the observatory. So when the blue wiggle meets the green wiggle, it means people are actively using it and you have no time left. On the other hand, when the blue wiggle is below the green wiggle, this is the time you could be using the observatory but aren't. That's where I get really upset. And come here and nudge you to like, hey, use the observatory. It's there for you, and I'll tell you how much it costs. But nevertheless, there are still times available. This is a little bit approximate. There is always a little glitches in the data, but you can see the point. If you wanted to use it, it's yours to use. It's not overly subscribed. And then the yellow wiggles are the moon phase. So, you know, we were trying to figure out early on how people would want to use this. We really didn't know. We were trying to see if there's a correlation between where the imagers still don't want to use it during the full illumination. In our setup, it actually doesn't matter all that much. We have narrowband filters, so I was trying to encourage people to use it no matter what. Just, you know, emphasize narrowband imaging. I don't see quite strong correlation here, but I just kept the wiggle just because it shows up. Now, some people do use it. So here are the top 10 observatory users. They're also the experts. So if you want to ever ask somebody, hey, what does that do? You can feel free to ask them. So you see that there are folks using it for, you know, hundreds and hundreds of hours of imaging. You know, this is just to tell you that it is available, it's there to use, and they're producing pretty amazing results. You'll see some of those in a minute. So this is just FYI how much time you can actually get. And people do collaborate online on the forum. We do have robotics observatory groups.io group, so if you can sign up, and most of the discussions happen in there. And people do collaborate on targets. So here are some of the top 8 targets that people like to image. I was really worried at first, like if everybody's going to like image one target because that's the most favorite object and we're just going to get one target ad infinitum. That's not happened. So there's quite a bit of variety. You can kind of see there's pretty tight clustering. There's not like one favorite, you know, target. And this is just top 8. There's like, you know, many dozens out there. So we've captured 28,000, this number, images so far in slightly over a year. So there's all of these images are available. I'll get to that in a second. We would have been paying for a lot of storage. We are now up to 2.4 terabytes of imagery in our archive. So if you want to play with existing targets and hone in your processing skills and not worry about the weather, like the cloudy sky LAS style, you have some data to play with. You can't really blame us for not having enough data. Now let's get to this. The background image is one of the images taken. In this case, thanks Paul for making this available to us. It's a fragment of a wonderful image. So let's talk about the usage policies. There are no policies. Anybody can use it. The only restriction we really have is like all raw data captured belongs to the club, and it's accessible to the club online at all times. So anybody can go in. It does take a little bit of learning how to use it. I hope it's not too complicated. If it is, it's my fault. But ultimately, anybody can go and ask for any targets that we've ever taken. They're all online. You can download them. Sometimes it may take some time to get them to you, but in general, they're all available. From processed images, people can use processed images however they like. They can share it with the club. They can sell them commercially. As long as there's reference and citation for LAS as a source of data, people can use images however they like. So where we've started a year ago, we've launched with, as I mentioned, full automated system. So all you need to do is go on the website, ask for it, and wait for it to show up. So it was pretty easy. We had fixed targets only at that point. We had online image and archive. So a lot of these things have been around for a year. They've been improved, I hope, and people have been getting usage out of them. And then we also have if you're into astrophotography, you know there is calibration involved. We have all this automated. When you take an image, you automatically get linked to the calibration images. It's fully bulletproof. Yeah, right. On the background is yet another image by Kareem taken with the observatory in process. Thank you for sharing, Kareem. In the past year, we've added quite a number of interesting features. 3i Atlas flew by and we wanted to capture it, so that gave me a kick to add moving target as a and asteroids as opportunities. So we now have ability to point and track moving targets. It works actually surprisingly well, but our equipment's pretty top notch, and we've been able to track 3I no problem, and many asteroids as well. So if you're into that kind of things, there are obviously difficulties with those, but we can do that. We've introduced cold archives. What that means is like we're not paying for 2.4 terabytes of storage. It's started to become pretty pricey. We now have a system where we take data offline, and it's called cold storage because you can always request the warm up, and the data will get to you automatically in about an hour or so. So it's a typical cloud-based storage thing, except we're not paying for any of it. And so that's kind of where we are today. What I would encourage you guys to do is to subscribe to the subgroup in groups.io. There's a community of folks that are using it. There are a couple of articles written when we launched it, one by me, one by our avid beta user, Martin. They would describe it to you in more detail how to make this happen, what it's all about. There are also tutorials on YouTube that I recorded, and a few sessions out there for you. All of those are linked in these messages, so feel free. That's about all I have.
Thank you, Roman, for that, and for the whole robotic observatory for that end. It is actually, no 30-second exposures, right? I did it. You did yell at me. Wasn't that long ago. Came out great, though. It came out really good. I don't regret it. But don't do it. Also, it was what he was saying about downloading data to practice processing is actually really, really cool, because you can get Cyril, I believe, is free. So you really have an entire processing, capture and processing channel for you for literally no price other than the $40 a year you pay for the club. Especially for if you're going to be processing narrowband, or you're going to be catching all your color channels one at a time. I've tried imaging that on my own rig once, and I can tell you I'm not ready for that. But it's super easy to do with the club stuff, and even better if just to download somebody else's. I did some jellyfish nebula thing that totally made it look like I knew exactly what I was doing, and that can be you as well. And my confidence was so high until I tried it on my own, and I got knocked down a peg. But it's a really great thing, and I would say it is I like to kind of throw it in as basically the crown jewel of our loaner program. That is a really, really awesome instrument, and if you were to rent such a thing outside of the club, I think it works out to $40 an hour rather than $40 a year. So we're lucky ducks to have that. And if you are, speaking of ducks, what a terrible segue. If you wish to wet your beak at shooting your own, at Lockwood we have the Rasa rig, so which is a ZWO based setup, and like for example this coming Saturday at Dark Sky Night. Oh wait, Eric's gonna use it. You can watch Eric use it, and he'll show you how to do it. Right? Yeah. No, it's great. He's gonna make it seem very accessible. But no, we have that. So if there's all manners of ways that you can catch your try different ways of astrophotography within the club, and now we also have a full stable full of smart telescopes for you to try out, be the ZWO stuff, the dwarf lab stuff. Anyway, so a lot of really cool opportunities for you should you want to take a piece of the sky home with you. All right. At this moment, I would like to make my proclamation of members that have done good deeds for the club. It is my Good Heavens segment. And for this month, I'll call out Shane Winter and Tim Thompson. You may recall You may recall that at this time last month, I mentioned that Monday was the first of an entire 7-day stretch that we had something going every single day of that week. As it would turn out, we had 10 things in 7 days, and I challenged all y'all to attend something on each of those 7 days, and Tim and Shane freaking did it. They were at the general meeting, they did school outreaches, they were at Garvey, they did Silver Lake, pretty much. He's old, all right? So like, so I gave him a pass. I said, if you FaceTime me while I'm at Silver Lake and describe what's in my telescope to somebody there, his ghostly presence was fulfilling to the people I was talking to. And I just left it at that. And he freaking did it. I was just sitting there, what the heck is this? And it was Tim. So it was awesome. My first FaceTime from Tim Thompson. So he did the dang thing. But yeah, they were at Mount Wilson, Dark Sky Nights at Lockwood, and the ill-fated Griffith Star Party that Sunday, featuring no stars, but but featuring Tim and Shane. Rest assured that they did receive their promised caloric reward that night. I offered a slice of pie, which they promptly ate. I will give an honorable mention for this for Andrew Inohara, who did 6 of 7. Yeah, 6-7. All right. So thank you to you guys for doing that. That was awesome. I believe I will do the upcoming events last. Should we do door prizes now? Let's do door prizes now. All right, for those of you that weren't paying attention, now is when you're going to want to wake up.
Who did not get a ticket? Anybody did not get a ticket? We all good? One up there didn't get one? Is that lady? I always got one. Yeah. All right, quick, okay. There, tickets officially in there. Make sure the numbers are there. And Justin, what are we giving away and how many?
Are you guys giving away any lasers or anything like that in person?
We do.
I mean, they have the option to choose a laser, or it's 50 on the store, right?
Correct, yeah.
Yeah, so it'll be 2. Yeah, so you have a choice here. If you want a green laser, you can have a green laser, or you get a $50 gift certificate at the Los Angeles Astronomical Society website gift shop online.
Yes, I'm going to give you that. Okay. And if you want a laser, just see Tim Thompson. He's giving it away anyhow. I'm just right. I'm kidding. Here we go. First number is 833-5637. Right up there. Okay, come on down, and if you would, give us, we have to get your name and your email, okay? And what is he getting? And what's the name? And your name? Manfred Dilsid. Good, congratulations. Okay, and the last one here. Is 833-5615. You're not excited. Okay, and your name? Jeff, okay. And make sure to get information is okay. Okay, and we have a laser here for you. Okay, we're good. So come see me and I'll get it to you, okay? And then the other two are for online, or? Okay, go ahead, Spencer, it's all yours.
Okay, so online, first one is Christine Tang. And let me get the second one. Dave Nakamoto, second one.
I'll take the gift card.
Ooh, I'll segue this. This is worth noting for those of you who weren't aware. The gift store has been restocked with a lot of cool stuff, including some Centennial merchandise, some Worm logo stuff, some classic stuff. It's worth giving it a new look. If you think you know what's on there, maybe you don't. Yeah, that's right. If you wanted a LAAS swimsuit, they're gone. They used to be there though.
They sold out.
We also got rid of the fanny pack. So R.I.P. LAAS fanny pack. Yeah, that was well, you know, it was there for 99 years. We had the first web store ever in 1926. Okay, enough. Too much joyousness going on here. Now I'm going to put you to work. The next one of these things is on the 13th of July. So if you liked this and you want to do it again, it'll be then. If you... We do know who the speaker is going to be.
Speaker is going to be Megan Lee. She's a PhD student from UCLA. She works on SETI. I think she's the only person doing a PhD on SETI data. She's amazing. She's also the organizer of Explore Your Universe, the enormous festival at UCLA. So come numerous.
Come see it. Or do it on Zoom, but come see it. You have a better chance of getting a green laser that way. Yeah, you can do it. You can be on Zoom from your seat. You can double your chance of winning something. That'll be a first, actually. You should do it, actually. You should totally do it. I want to see. That would be awesome. Like, absolutely do it. I'll call you out. No. He invented it. You can get it once. All right, beyond that, we have our Griffith Star Party this year, which I'm not going to give you the date for, unfortunately, because it's going to be another abbreviated one. And given the short amount, the brief amount of people who are allowed to have that, I'm going to be reaching out to our stalwarts of the Griffith Star Party, and it'll be them that get to go for this one. However, another opportunity is coming up for you to be in front of a lot of people with your telescope, which I will get to you in a moment. Our next Silver Lake outreach is going to be this Thursday, as every Thursday. But our next big one is going to be on the 18th. We had family night last Saturday, which was so amazing. The next one of those is going to be on July 25th. Dark Sky Night this Saturday. Come on, you got to go. It's going to be awesome. It wasn't that cold last week, and the sky was pretty good. We have a new member potluck and swap meet coming up at Garvey on the 27th. I know.
Hey, sorry, Keith, you're muted.
Me?
Yeah, okay, you're okay now.
Weird. We have upcoming LIGO tour at Caltech on 7/12. I believe the first one of those blurbs went out to you via email. This is going to be Gabriella, who was one of our past speakers, is going to be giving us a tour. It's a limited amount of people to do it, so do sign up. 40? It's going to be 40. All right, great. So sign up to do it. Not yet, but just brace yourself. He's feeling lucky right now because he got his flippin' laser. Okay, so the other stuff I was talking about is the American Astronomical Society is having their convention in Pasadena in the coming, I guess, next week. And because we are awesome and rad, and by we I mean only you, we have been invited to participate in star parties for 2 of the dates. The first of those is going to be this coming Sunday, which is going to be solar only to participate in the City of Astronomy event, I suppose. Yeah, event. Yeah. It's a Caltech thing, so you can say you worked with Caltech, which is always a cool thing to do. Save it for Thanksgiving to talk to your relatives and say, I'd work with Caltech. Except for those of you that always work with Caltech, so it's not impressive anymore. But a lot of us haven't done it. Freaking nerds. And the other one is going to be on the Tuesday, the 16th. And that is just part of the standard fare of Amateur Astronomer Society. But that's actually, the one on the Sunday is going to be solar only. If you come on Tuesday, the 16th, you can show people the cosmos outside of the sun. Details forthcoming. But that's something we don't normally get to do, so if you are bummed about not being able to do Griffith, do this instead. Our next board meeting is going to be Wednesday, 7/8. Somebody actually did it. Jimmy C. showed up at the last board meeting, and he stayed for the whole thing. Bless his heart. And then if you go to Lockwood this coming Saturday and say, this is amazing, I want to put my fingerprint on this thing, the Lockwood Committee meeting is going to be on 7/6. And there is not any requirements for that other than being a member. So just sign up for the Lockwood Committee and take part in the shaping of it. We have a lot of really cool stuff coming up this year for expansion. We have a budget. We're going to use it, and it's going to be great. You're going to love it. And with that, we're done. No. Nope, Dark Sky Night is for everybody. It's for lovers. What's that? Oh, shoot, you're right. I'm so sorry, Andy. Yes, also, we're doing one of our Mount Wilson star parties this Friday, which is super, super cool. Yeah, look for the details. You've been blasted about it already. It's in your email box. But you should come. They've been really good this year. With any luck, we'll get the Marine layer to wipe out the city again, and you'll feel like a sky god, I promise. Okay. All right, everybody go home.